All right, so again, what we're going to do is we're going to just talk about the basic math, and we're going to talk about some things that are not going to be on this test. So, and I'll tell you what those are when we get to them. And some of this is not going to be on the test. I'm just trying to bring some context to it and show you what it is that we're going to use some of the basic math for later in the semester. So we're going to talk about it, and I'm going to show it to you, but at the same time, I might give you a little bit of a preview and a hint as to how we're going to simplify some of this math, because there is algebra in the curriculum, there is math, basic math, but some of the principles that we have to know, and these are things that you really should know for clinicals and certainly for the registry. Most of the math that's going to be on the registry is stuff that you can work in your head if you know how the concepts work, okay? So you're going to have algebra on the registry, but if you know how, like the inverse square law, direct square law work, you know, you can, unless it gives you strange distances, you can work it out almost in your head. Some of you will easily be able to work it out in your head. Some of you will have to use calculator, and you can use calculator on the registry. Okay, so even though it sounds scary, you know, the math terrifies people. Algebra absolutely terrifies most people. But the true amount of math that you're going to have to know, even through the registry, is not as much as what you would think. And there are shortcuts and you know, ways to get around it. So that's what I'm going to show you today. So we're just going to pick up with chapter 2, basic math. You know what fractions are. Fractions are a portion of a whole. So a half would be represented as 1 over 2. That's a half, and that is 50% of a whole. In a decimal form, how you would get to a decimal form from this is divide the numerator by the denominator, and what you would have is 0.5. So really decimals and fractions are the same thing, they're just represented differently, right? So decimal would be anything, you know, you got the decimal point, and then anything to the right or left of that, you'd have numbers. If you have anything to the left, then you've got whole numbers. Anything to the right, you've got, you know, basically a fraction, right? So 0.5 is a fraction, it just means 1/2. 0.1, how we express that aside from saying 0.1? It's 1/10, right? So then again, we're right back to a fraction, right? So 1/10 equals 0.1. So if we had 0.2, that would be the same as 2/10, but is that a proper fraction? No. No, it's not. So to get to a proper fraction, what you need to do is you need to break it down to its smallest form. Right, so what you would do is you would divide that out and you would have 1/5. So all of those mean the same thing, right? So if you have a question on a math test, and you're not going to have a written math test, you know, every test this semester is going to be multiple choice, but this semester, next year, you're going to have a written math test. So you got to calculate things out, and you'll have to break it down to the smallest possible fraction. Okay, so decimals, fractions are really pretty much the same thing, and taking it out a step further, percentages are nothing more than a fraction or a decimal, right? So 100%, for example, is the same thing as 1. If you have 100% of something, how much of it do you have? All of it. All of it. If anybody ever play sports? Okay. So your coach told you what? He wants you to give 110%. Is that possible? No, it's not possible to give 110%. You know, but if he told you to give 100%, well, I did the best I could do. But most likely you did not. You know, you brought it up to the point you were comfortable with, and then try to draw extra out of you. Your 100% is usually much greater than what you think you are capable of. Your body is capable of some ridiculous things if you push it hard enough, right? And that's what he was trying to do, is 110% is really trying to get you to that 100%. So if we had 110%, then what we have is 1.1. It's just decimal, is all it is. So if you had a bank account that was earning 10%, then at the end of the year, what that means is you would have 110% of your original value. Good luck with a bank account that pays 10%. Some of the online things you might get 4%, but most of them are maybe 0.1% local. So fractions, decimals, percentages, just all ways to reflect a more precise number. Be it larger than the original or be it smaller than the original, it's just a way to express those things. So you may have to add, subtract, multiply, or divide. We're just going to go with percentages, with fractions, because with decimals, it's just line them up. Just line up the decimal, add the numbers, and you got it. But with fractions, it gets a little bit more complicated. So if you're adding 1/2 plus 1/2, how do you solve that? Yeah, add your numerators, and what do you do with denominators? They stay the same, right. So what you have there then is 2 halves, so you've got 1. Right, so you got a whole, but it gets a little bit more complicated when we do something crazy like 1/2 plus 1/3. So how do you solve for that? You got to find a common denominator. You can't add that, right? So what you have to do is find a common denominator. And kind of the cheat code here, if you don't really want to work out the lowest possible common denominator before adding them up, is you can multiply the two together and it would be the same. But what you would have to do is multiply both by whatever you multiply it by, right? So if in this case our lowest possible common denominator would be 6, okay? So if you multiply 2 times 2, you get to 4, and that's not the same as 3, right? So 2 times 3 would be 6, and then 2 times 3 would be 6. So what we would need to do then is to multiply this by 1. Is that 1? Mm-hmm. Yeah, 3 over 3 is 1, right? So then what we would have on this side is we would have 3/6, and over here we would need to do the same thing, except for to bring that to 6, we would need to multiply by 2 over 2. So then that would be obviously 1, and it'd be 2/6. So we can just kind of get rid of all of that right there and say 3/6 plus 2/6 would be 5/6, right? You don't have to set it up like that. It's just the easiest way for me to get to it up here. Okay, so addition, subtraction, find the common denominator. Multiplication and division, you don't have to. With multiplication and division, you just go straight across. All right, so using the same numbers, and what you'll find this semester is, and next semester, is if there is a way to simplify an equation, I'm going to simplify the equation for demonstration purposes, okay? So I'm going to use easy numbers here until we get to the point where numbers get a little bit more difficult. So using the same thing, if we have 1/2 times 1/2, then what do we have? We multiply straight across and we've got 1/4, right? So 1 times 1 is 1, 2 times 2 is 4, so we've got 1/4. It actually got smaller, right? So with division, it's a little bit different. If we have 1/2 divided by 1/2, then what do?
You inverse the second.
You can do one of two things. You can either cross multiply, which we'll get to here in a minute, or you inverse the second half of it. So we have 2 over 1. And so what do we have now? Yeah. Invert and then you multiply. Right. And now what do we have? 2 over 2, which is 1. Right. Okay, so we see the division set up sometimes a little bit differently than what I demonstrated up here, and that is with what we refer to as ratio problems. Okay, A ratio problem is a problem where we're comparing two things. All right, so we talked about this last week, and what are your rules for your radiation safety? 3 things: time, distance, shielding, right? So time, sometimes you can do something about it, sometimes you can't. If you're in a fluoro case, you can't do anything about it. Shielding, if you have to be in the room, you need to be wearing a lead apron. If if you feel like it and you can find a pair of those little leaded glasses, you can put those on. They're horn rimmed. They're not going to make you look attractive at all. But they're protection, and they've even got some lead strips in the temple area. You can find those. You can also put on a thyroid shield as well. What you'll find in lead aprons in specialty areas where they can't keep their face facing the radiation source, which would be the patient, they'll have wraparound aprons. So places like interventional radiography, cardiac catheterization, and special procedures, you'll see wraparound aprons. In diagnostic, a couple of things. One is our aprons are one-sided, and we always tell you keep your face, anytime the machine is activated and you're creating x-rays, face the patient. All right? Why is that?
The shield.
Yeah, because your radiation protection is right in the front. I have literally seen people get stuck inside of a room. Not truly get stuck, but be present in a room without an apron on, and they hear the fluoro kick off, and they immediately turn and face the patient, not wearing an apron. Is that wise? No, it's stupid, right? So you got to apply a little bit of, thinking here. Why do we face the patient? Well, because you got lead on. If you don't have lead on and you hear the fluoro kick off, what are you going to do? Quick step it out of the room with your back to the patient, right? Just get out of the room. Don't turn around and face the patient. That applies only if you're truly leaded. You shouldn't be in a room anyway, unleaded, if there's a chance of fluoro's going to kick off. So that's a kind of a rabbit trail and a bit of a rant there, but don't make that mistake. I've literally seen people walking out of the room, they hear fluoro come off, they turn, face the patient, stop. Use a little bit of common sense. All right, so we got time and we've got shielding, and what's the other thing? Distance. So we have 2 laws regarding distance. One is what we refer to as the inverse square law, and one's a direct square law. Now, I'm going to simplify this again, and then we're going to look at real world practical applications here. So, and this is not on the test, this is so that you see where we're going later in this semester and next semester, and also in imaging. Amy's going to drop this on you later in the semester, okay? So the inverse square law says that the radiation intensity is inversely proportional to the square of a change in distance, okay? So what we're looking at is intensity of the radiation field. So if we go with I1, original intensity, over I2 is equal to the inverse of the change in the distance, okay? So if it's inverse, we're going to go with distance 2 over distance 1, and then we're going to square the whole thing, okay? So if I said that my original intensity was 1, and I didn't know what my new intensity was, but my original distance was, common distance that you're going to shoot with is 40 inches, right? And for simplicity's sake, I'm going to say that we're, instead of going from 40 to 72 inches, I'll get there here in a second, I'm going to go with 80 inches, okay? And then you can square it. Now, you can work this a couple of different ways. The order of operation is PEDMAS, parenthesis, exponent, the whole thing. So whether or not you get rid of the parenthesis or you do the exponents first, really, in this case, it does not matter. You know, you can work it either way. Don't get too uptight with how I work it versus how it might need to be worked according to, it doesn't matter. It comes out exactly the same. So, let's see, calculator. So, what we're going to do is we're going to handle this side over here, and we're going to get rid of the brackets, and we're going to get rid of the exponents. So 8 times 8 is what? 64. All right, so what we have then is 6,400 over 4 times 4 is 16. So we've got 1,600 is equal to 1 over x. Now this is a ratio type problem, so you're comparing different things. You got different things across from each other. This is what we refer to as ratio type problem. At this point, what we do is we cross multiply and we solve for the unknown. This is algebra, okay? And I'm gonna go over here so that y'all aren't having a crane neck, but this is algebra. All algebra is solving for the unknown, and algebra scares you to death. But you know, my kids. When do they start putting letters in math? I'm never going to use that. You use algebra every day. Every day. You go to the grocery store and you've got $10 on you, and you know, I don't know, oranges are 6 for $4. How are you going to figure out how many oranges that you can buy? You solve for the unknown. Exactly. It's algebra. Okay? So we're not going to work that out. But what do you do at this point? Cross multiply and divide, right? So 1 times 1,600 is 1,600. And so that would be 1,600 is equal to 6,400 x. Now what do you do? Divide by 6,400. Divide both sides by 6,400. And what you're going to have then is, and if you got a calculator out, you should have come up with oh, no, I just did that exactly the opposite way, which is the direct square law. 1/4 is equal to x. Radiation intensity decreases with a square of the change in distance. How much of a change in distance do we have? A factor of 2.
Yeah.
2 squared is 4. So if we double our distance, if you take a study, you're getting so much radiation 1 foot away from the patient, you're doing a fluoro case, and you back up to 2 feet, how much does your radiation intensity, how much of a change in exposure to you do you get? It drops by a factor of 4, right? Pretty significant, right? Now this is what we refer to as the inverse square law. What's a law?
It's like a theory, but it's proven.
Happens every single time. Okay? So you get an inverse square law that you double your distance. You double, and again, this is not on this test. But file this away, right? You get a inverse square law question. The question's asking you how much intensity do you have if you increase your distance from 40 to 80 inches? What's it gonna be every single time? Factor of 4, right? So let's do this differently a little bit. Let's say you went from 20 to 40. So now what do you have down here? 4 times 4 is? So we have 1,600 over 400, right? It's a little bit easier to work out. 1,600, change these around. Now we're going to divide both sides by 1,600. 1,600. I don't know how you even have to change the answer. It's exactly the same. Why? Because it's inverse square law. Right. Okay, what's the problem with this? Where are your distances? 40 and why couldn't they make it 80? Just why, you know? I mean, that 8 inches really gonna be that much of a problem for anything? No, it's not, but we're gonna land on 72 inches. So let's redo this and let's use our practical distances. So we have I1 over, we don't know what our new radiation exposure is going to be. Distance 2, we're going to back up from 40 to 72 inches. So we know most of this. The only unknown is what is 72 going to be squared. Somebody with a calculator, get on it. You got your phone out. Just use a calculator on your phone. I'm going to go ahead and bring it over here. 1,600. Who's got it?
5,184.
5,184. All right, so then we have 1,600 is equal to 5,184x. Divide both sides by 5,184. 5,184. X is equal to, who had it? I just say 3.24. 3.24 is the answer. Okay. What's it going to be every time? 3.2, because it's inverse square law. Every single time you back up from 40 to 72 inches, then your radiation dose is going to change by a factor of 3.24. How many times?
Every time.
Every single time. Every single. Do you have to work out the inverse square law ever again for this particular set of circumstances? If you go from one distance to double the distance, what's going to happen? Every single time. Factor of 4. Every single time. Do you have to work that out ever again? No. Okay, so let's go in the opposite direction with it. You're in the middle of fluoro, and you've done, you know, in your head you've done this. Okay, if I back up just a little bit, my radiation intensity is going to drop. And right about that time that you're feeling good about your radiation dose, radiologist says, give them, you know, some thick barium. What do you got to do? You got to step up, right? Give the patient the barium. What happened if you decreased your distance from 40 to 20? Increased by a factor of 4 every single time. Every single time. It just goes in the same, you know, it's the same thing, just opposite direction. Every single time you cut the distance in half and your radiation dose goes up because it's inverse square law, right? So you decrease distance, intensity goes up. No. I think I just said that backwards. You decrease distance, intensity goes up. You increase distance, intensity goes down. So you hand the patient the barium, what do you do now?
Walk away.
Walk away, exactly. Step back again, right? Unless, you know, sometimes you have to stay there because, you know, the patient, they can't cooperate, can't get to the straw, something like that, you know, so sometimes you have to be there. But when you can, you need to step away from the table. Okay? So 3.24 is changed from 40 to 72, 72 to 40 is always going to be 3.24. All right, so at some point, you know, especially this time next year, I'm going to give you some weird distances, 40 to 60 inches. I may just change it by 4 inches. You'll have to work out the inverse square law. But for these distances, you never have to do that. And most of the questions on the registry are going to come at you from these distances or something similar. You're going to double your distance. Your radiation intensity is going to drop by a factor of 2. Of 4. Drop by a factor of 4. Okay? So what does this mean from an imaging standpoint? And this is probably what Amy's going to stress this semester. She's going to stress the inverse square law next semester on radiation safety. All right, so you make the perfect exposure on a patient at 40 inches. Okay, so let me back up just a little bit. For the most part, this is going to be your dose calculation equation, the inverse square law. So, you know, your questions will ask you, you know, you receive 2 MR at 1 foot, 2 MR per hour at 1 foot, let's say. If you increase your distance to 2 feet, What's your new dose? You divide by 4. Right, you divide by 4, so it'd be half. All right, so that should be in your mind when you see dose. We're talking inverse square law. But there's a technical factor consideration here as well. What are you losing here? Well, you're not losing KVP. KVP is really unaffected by the inverse square law. Okay, KVP, it just, you know, it remains the same. So what we're losing is numbers, quantity. Quantity is mass, okay? So if I shoot the perfect exposure at 40 inches, let's say, you know, the patient's in ICU, and all I can do is portable chest x-ray on this patient, they're laying flat on their back, you can only get 40 inches. So I shoot the perfect exposure on the patient at 40 inches today, and they're doing better tomorrow, so you can set them up and you can shoot them at 72 inches. You know, you test an over chest x-ray, you want to shoot them at 72 inches. Why? Decreased magnification of the heart, exactly. So you can get back to 72 inches. If you can get back to 72 inches, you want to get back to 72 inches. So you know you shot the perfect technique yesterday at 40 inches, you go to 72 inches, and you don't change your technique from what you did yesterday, what are you going to have? Just in a word, 2 words really. You going to have enough radiation for the patient to make a good exposure? No. Okay, so this is what Amy's probably going to stress this semester, and that is what we refer to as the square law, the density maintenance formula, or the direct square law. Okay, so what we have then is, that's one of the dilapidated ones. Where'd I put mine? Mass. What does mass control? Quantity is a quantity. It's what we use to control quantity. So you back up distance, you lose quantity. Okay, so mass 1 over mass 2, it is the direct square law. So what we're going to have is D1 over D2. This formula, let me get rid of, we already did the math on this, so it was, let's see, D1 was 40, D2 was 72, right? So, so now, what are we going to do? We had one mass before. Yesterday was perfect at 40 inches. Now we're at 72 inches. Okay, what's our first step here?
Square.
Square. So we're going to go 1,600, and you can divide that out if you want to. This is easier for me. 1,600 over 5184 is equal to 1 over x. 1,600x is equal to 5184 divided by 1,600 divided by 1,600. What do you suppose our what do you think we're going to have over here? 3.24. It's 3.24. 3.24. Okay? So now our new mass is identical to how much radiation we lost when we backed up from 40 to 72 inches. Does that make sense? Because you increased your distance, because you increased your distance from 40 to 72 inches, you're gonna need the same amount of change in your technique as the amount of radiation you lost because of that increase in distance. That's why it's density maintenance. You're maintaining the density, you're maintaining the exposure to the image receptor because of that increase in distance. Yeah?
I was just a bit confused on how we got to 3.24 when dividing 1,600 by 5184.
So divide 5184 in, or by 1,600
For the inverse.
for the inverse square law.
Yeah, when you had the 1600
Okay, yeah, okay. It probably should have been this.
Okay.
Yeah, yeah. Yeah. I got excited, got ahead of myself, you know? Yeah. Okay? So you're right, and thanks for pointing that out. In the original, when we increased our distance from 40 to 72 inches, then our exposure was 3.2 fourths. Yeah, thank you.
Bless you.
Bless you. And because we decreased that, then we have to increase to reintroduce that radiation back to the image receptor. So these questions are coming at you from a different standpoint. The inverse square law, when you work the inverse square law, your intensity is going to go down with an increase in distance, right? Your exposure is going to go down by increase in distance. And what that's, again, the questions are going to ask you, your radiation exposure, the patient's radiation exposure is this much at this distance. You change that distance, what's your new exposure? These are gonna say mass. You shot an x-ray with whatever mass, what's your new mass if you change your distance? If your distance goes up, what are you gonna have to do? Multiply by 3.24. If your distance goes down, what are you gonna have to do? Divide by 3.24. Now, how many times are you gonna have to work this out for 40 to 72 or 72 to 40? I mean, this whole thing? All you gotta do is remember this. So if your distance doubles, what do you gotta do? Multiply by a factor of 4. Yeah, and yeah, somebody said 2. Somebody said 2, and you're gonna make that mistake. You're gonna say, okay, you increase. It's equal all across the board. It's not. It's exponential. It's squared. It's distance change squared. How much of a change in distance?
2.
What's squared?
4.
4. Right. Okay? All right? Okay. I got a couple of giggles there. I don't know if that's a vulgar, hand signal or not, but
No.
okay. All right. Okay. All right. So always that. Okay? So we just did a whole lot there. We just did algebra, we did, fractions, we did decimals, conversion of
Exponent.
fractions. Yeah, exponent, everything. We did pretty much all of this. Okay. Any questions on that?
Is that gonna be on the test?
No, not this test. No.
Yeah.
No. I don't think there's any math on this test. I think really this test primarily is once it gets into there may be some definitions. Even okay, so if you flip over to page 26, you see from 26 to the end of the chapter, a lot of equations. And just put your mind at ease. You're going to have to recognize those equations by description, okay? You're not gonna have to work them. Huh? You're gonna have to recognize the equations by description of the equation, but you're not gonna have to work them out. So there's no math on it. It's just like velocity. What is velocity?
Distance divided by time.
Yeah, what's an example of velocity? Miles per hour. Yeah, right.
Are you going to use like an example, like if a car is going this fast and then it decelerates to this speed, which formula would you use? Okay.
No, it's just straight definition, it's just straight identification. What is the, formula for velocity? What are the components probably would be a better way to describe it. I give you the components, or definition, maybe common definition of speed. That's velocity. What is velocity? It's distance over time. Distance traveled over time. Yeah. But no word problems, no math, that's just, and the reason we're going through this is because most of these are applicable in some way or another by their definition. Maybe not as far as calculation goes, but by their definition, for example, okay, so this is getting ahead of it. Let's say acceleration. Let's pick acceleration out of there. What is acceleration? You're driving down the road, you're behind a tractor. This is East Texas. It happens.
Yes.
You're driving down the road, you want to do 70, but you're behind this tractor doing 30. What do you want to do?
Accelerate.
You want to pass him. How do you pass him? You gotta gain speed, right? So what pedal do you mash? The brake? The accelerator, right? So accelerator is yeah, exactly. Bless my wife's heart. You know, I get a little impatient on the road and get a little aggressive sometimes. She's hanging on to the, we call it the OS bar. I'll leave it to you to work out what that is. But anyway, she's like, stop. I was like, he needs to know he's an idiot. I gotta get running as fast as I can, you know. He needs to know this. I need to educate him. but
That's what I do.
see, you're doing God's work. You're letting people know, you know, they need to know these things. You're an idiot. No, but yeah, at the same time, I get chewed out a little. Okay, so acceleration, change in velocity. You're going one speed, you want to go another speed, you have to accelerate, you have to get up to speed. Okay, so acceleration is a change in velocity, and that is probably how that question will come at you on the test. Is what acceleration could be defined as change in velocity, right? Change in velocity, something like that. Okay. What's our time? What time did we start? Well, we're going a little longer than I thought. Okay, so do we have any questions on really kind of the just the basic math? So as far as the exponents go, and to make you understand a little bit better of some of the stuff that I've kind of preached on a little bit, is how, I've said that X-ray creation is very inefficient, right? The main thing that we create in an X-ray tube is heat. We got heat. That's the primary thing. We create a little bit of light and even fewer X-rays, and it's extremely inefficient. So what we measure our technical factors in, we've got the power of the X-ray beam, that's your KVP, so that really doesn't play into this, but the other is mass. Mass is a measure of electrons, it's just a number of electrons, okay? And it's a lot of electrons. So the definition of an amp is a coulomb of electricity. Coulomb's a measure of power flowing through a circuit, and it's 1 amp per second, okay? So that's an amp, and we work in milliamperage, so it's, it's a number, a quantity of electrons is all amperage and milliamperage is. So I say it's ineffective, or it's inefficient. It's not ineffective, it's very effective, but it's inefficient, the way we create X-rays. So let's say we have a 1 mass exposure. Okay, so what does that mean? What is 1 mass? What is an M? Milli, which is 1/1000, right? So I think I've said, a rough estimate, especially at low KVP values, what percentage of our X-ray beam becomes, or what percentage of the electrons we send across the X-ray beam actually become X-rays?
1%.
1%, right. So it gets higher as KVP goes up, but we're going to go with 1%. Now, what is an amp? Well, it's a lot of electrons. So, again, this is not on the test. I want to make sure I get the exponents right. But 1 amp is 6.4 times 10 to the 18th power electrons. Yeah, that's a lot. So what we have here then is 6, and how we would write this out, all exponents are is a way to express big numbers with little numbers. That's it. So we've got 6, and to calculate this out, what we will do is move our decimal place 18 times. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 8. That'd be 1,000 mass exposure. Where are you going to use 1,000 mass exposure? I hope you never do. Right? That's a big exposure. But we need 1 mass, which is 1/1000th of this. So if I divide that by 1,000, the easiest thing to do would be to just knock 3 zeros off, right? And if only 1% of that becomes X-rays, I can knock 2 more off. So how many X-rays do we create with 1,000? Well, with a 1 mass exposure? A big freaking number, right? So what if only 1% of those are useful X-rays? What do I still have? Another big freaking number, right? So is it ineffective? No. Is it inefficient? Oh, yeah. Yeah, it's very inefficient. But we still got a lot of X-rays left, right? So how we would express that in scientific notation, again, would be 6.4 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 10 to the 11th power. Still a lot of X-rays, right?
Bless you.
Bless you. So exponents can go in the opposite direction too. So if you have, Bushong introduces the concept of Planck's constant, which we'll get into later in the semester, and it goes into the frequency and wavelength of X-ray photons. And what we'll talk about is the electromagnetic spectrum. Any kind of light waves travel in a sinusoidal waveform, and the longer that waveform is, the lower the energy is. So X-rays, gamma rays, very, very short waveform, and Planck's constant goes in the opposite direction, and it's 0.07 times 10 to the, 663 times 10 to the negative, I think 34th power or something like that. So what we've got there is 0.00000 and a lot more O's, 663 or something like that. So how that would be expressed is 6.63 times 10 to the negative 34th power. All right. So positive exponents, negative exponents. Positive exponents will move the decimal to the right. Negative exponents will move it to the left. And in both cases, it works out to be the same. Just where the decimal is, count the numbers. Yeah. And if it's positive number, then you got a positive number. If it goes, if you're less than a whole, then it's going to be a negative exponent. Okay. Just other couple of little housekeeping things. 10 to the 0th power, 1, 10 to the first power equals 10, and then it goes truly exponential after that. 10 squared equals 100 and so on. So you just count the zeros essentially. Right. You can add them, subtract them, multiply them, divide them. If you multiply them, then you just, like if we had 6.4 to the times 10 to the 12th power, you just add them together, So it would be the 30th power, right? Very simple. Any questions?